Now let's look at an example of a simplification of a system of parallel forces. So this is where you've got a 2D plate or whatever you've got, and you've got forces acting parallel to each other and perpendicular to the plate. So here all these forces are acting in the y direction, and they're acting on a plate that is in the xz plane. Okay, and I've got 6 kilonewtons acting down at, 0.3 meters over in the x and 0.5 meters out in the z. I've got a 5 kilonewton force acting down. That is 0.6 meters in the x and 0.7 meters in the z. And then over here, I have a 1 kilonewton force acting up in the positive y. And it is sitting right there on the x-axis at a distance of 0.8 meters from the origin. We want to take all of this and turn it into that. Easier, right? Easier to look at, easier to visualize. So that's the whole point here, is we're just moving around and manipulating these vectors to get them simplified down without any loss of any of the forces or moments. You know, we can't just throw stuff away. We're just simplifying it. So the first step, find that resultant force. This is the easy part for these when their forces are parallel, because they're just, you can just add their magnitudes together. So I've got down is negative, up is positive, so I have -6. -5 plus 1. So that's going to give me minus 10 kilonewtons, or 10 kilonewtons acting downward. So that's my resultant force. Now we're just going to have to figure out, you know, that's the value of that vector right there. We just now need to figure out exactly where to place it. It's got to be placed such that the moment caused about the x-axis and the z-axis are the same for this system on the left as it is for this system on the right. Neither system is going to cause moment about the y-axis because the forces are all parallel to the y-axis. Okay, so let's calculate the moments of our original system. So about the x-axis, which is this one up here, we're going to have 6 kilonewtons times 0.5 meters, and that's going to be a positive moment because at right-hand rule, put the base of your hand at the origin here and stick your thumb in the direction of the axis. Your fingers are going to tell you which way is positive moment. The 6 kilonewtons pointing down, just like your fingertips are pointing down. So you know it's going to be a positive 6 times 0.5. And then you're going to look at this force right here, which is also going to be a positive moment, 5 times 0.7. And then the 1 kilonewton force is acting through the x-axis, so we get no impact. Okay, so that gives my moment about the x-axis due to these three forces equal to 6.5 kilonewton meters. And it's positive, which means that it is a counterclockwise moment about that axis according to the right-hand rule. Now, about the y-axis, like I said before, there is no moment. All the forces are parallel to it, so they can't generate moment about it. Now, about the z-axis, which is this one over here. Stick the base of your hand at the origin, point your thumb in the direction of the z-axis, and then your fingertips will point in the direction of a positive moment. You can see that the 6 kilonewtons and the 5 kilonewtons are both going to be wanting to cause negative moments. The 1 kilonewton will want to cause a positive moment. So now we just fill in the blanks. 6 kilonewtons times the perpendicular distance from the z-axis is 0.3. Then I've got 5 kilonewtons times its perpendicular distance from the z-axis is 0.6. And then 1 kilonewton with its perpendicular distance from the z-axis is 0.8. Add all those together, I get minus 4 kilonewton meters, which means in general, the moment is going to be clockwise, which makes sense because the 6 kilonewton and the 5 kilonewton are really a lot of force pushing down. It's going to want to be cranking this plate clockwise about the z-axis. So that those signs make sense to me. So now we have this, which is a force and two moment vectors. And remember, I will take a little aside here and say, you know, you can always simplify it down to a force resultant and one moment vector. And you're like, well, wait, you've got two moment vectors. Keep in mind, you can find the resultant moment vector as the square root of the sum of the squares of these two. But I didn't do that because that's not what I'm asking for in this problem. I'm actually asking for simplifying it down to one force at just the right location. So I'm going to leave it in its components like this. So there's my 6.5 and my 4. Remember the 4 was negative before, but see how I've drawn my moment vector? I've drawn it clockwise. So I got rid of the negative sign because I showed the vector correctly. So for the x-axis, we have 6.5 kilonewton meters, and we have this 10 kilonewton force. So if we start moving this out in the z, we can move it just the right distance to generate the right moment. What's that moment? 6.5 kilonewton meters. So I have 6.5 kilonewton meters is equal to 10 kilonewtons times some distance in the z. What is that? 6.5 divided by 10, solve for d sub z, right? D sub z is 0.65 meters. And then let's do the same thing again about the z-axis. So now we're dealing with this 4 kilonewton meters. 4 kilonewton meters is equal to 10 kilonewtons times d sub x. Solve for d sub x, you get 0.4. So I'm showing the 3 equivalent systems. The one down here is actually the final answer, what it was asking for, but this intermediate one was also another equivalent system. Right? So we had this system, the original, this intermediate system, which is equivalent to it, and then the bottom one, which is our answer, equivalent to both of those other ones. So these are all 3 different ways of showing a force system that gives the exact same amount of force and moment about the origin.